Let us recall in lecture 10, here I was talking about dehomonization and homonization. So, so if you start with suppose two polynomials, R and S, these are two polynomial rings, one in n variable, one in n plus 1 variable. Then what is there? So if you take some polynomial in R, you can homogenize, right? So this is what I denoted by this hom if, and this will be a degree D homogeneous polynomial. So this will be a degree D. If f is a degree D polynomial, this is a degree D homogeneous polynomial. And if you take a degree D homogeneous polynomial, and if you dehomogenize, then this will be degree less than degree D, less than or equal to. So this will be in R less than equal to D. So R less than equal to D means degree of the polynomial is less than D, less than equal to D. And the point is that if you start with some degree D polynomial, there is a homogeneous polynomial such that if you dehomogenize, you get the polynomial back f. And of course, this I is important because you are dividing by xi. So that's why I keep I. Okay. So I leave you this as exercise, and I will use this to prove this this theorem, this proposition. So with the ultimate goal, so we are yeah. So what is it? So it says that if you take a closed subset, algebraic subset in Pn, then you have this map psi I, which is a map from An to Ui. Then psi I inverse of x intersection Ui is this, you can write it as a closed subset in An. And here the other one says that if I start with some closed subset in An, so now if you take the image psi I of Vi, this is basically its closure is the homogenization of I. Yeah. So and as a consequence, you will see. Okay, I'll briefly sketch the proof. So proof sketch. So one there is nothing. One is obvious. I will not draw it. And if you just see, this follows from definition. And in 2 is little tricky, but 2 is that if we take the ideal I, which is in K y1, y2, yn, then if you consider the closed subset Z, which is 0 set of homogenize the ideal I, then the point is that Z intersection Ui is nothing but psi I of y, and Z will be something like Z is, and this will be nothing but psi I of y, but this is a closed subset and this is a closure in Pn. And the Z intersection Ui, so that is a closed subset in Ui. So now what that means that, so 1 and 2 will say that psi I is a bijection, and it takes its inverse image of closed set is closed and image of closed set is closed. So that will say that psi I is a homomorphism. So So this again. I am not doing this checking. So these are the two things. This is you see. So to show that Z is psi I Y closure, you prove that first you prove that Z is a sub of psi I Y bar, and then the other way. So I am leaving this as exercise. I am not doing details. Okay, I am leaving this. And then 1 and 2 of course will imply that, because that will say that psi I is a bijection. So 1 plus 2 will imply 3. That it's a homeomorphism. Okay. So, but this is a very important proposition. It require you need to do it yourself. Yeah. Okay. You do it, because this is very important. Don't leave it. So, but this is the point. Okay. So before I go ahead, see, now you define projective variety. So you define projective space P and K, and you define a Zariski topology on it. Now if I take a closed subset Y, I can give an induced topology, right? And you have this, all these definition makes sense, that irreducible closed subset, because irreducibility after all is a topological definition. So if you have a topological space, if you take a subspace, you can closed subset, you can ask whether it is irreducible. So irreducible closed subset, I call it projective variety. So irreducible. So this is definition, irreducible closed subset of Pn. It's called projective variety. So this is definition. And just like the dimension of a topological space makes sense, so dimension, everything makes sense here. And but one thing I should say, what is ideal of the definition. Like in affine case, if you take a subset Y in An, you define Iy. Exactly similar way here you can define. I'll come to that. But so this is, and this is one, and another thing, that the open subset of projective variety. Dimension of a variety I did not. Dimension of a topological space I defined, right? Y1, Y2, Yn. Increasing chain of, yeah, irreducible closed subset. No. Open sub. Okay, I'll define them. Huh? Yeah, when I said that height of prime ideal and dimension of the ring and dimension of the dimension of a topological space is, I did not define. Okay, open subset of projective variety called quasi-projective variety. So dimension, so if X is a topological space, Noetherian say, then you define dimension of X is supremum of n, x0, x1, xn equal to x. So any chain will stop because it's a Noetherian topological space. These are all closed subsets. So you define like this. So Yeah, you can take irreducible. Even you don't need that, but anyway, you can take irreducible. Irreducible plus subsets.
Then how xn will be, x will be irreducible?
Yeah. So this is first you define
All the x's should be irreducible closer. Then when it
no.
xn will be x.
See this Noetherian topological space. If X is a Noetherian topological space, you can write it as X1 union X finitely many, right? X1 union X2 Xn. Then now a dimension of X will be maximum of the dimension of Xi. Suppose it's a disk and a line union. Then the dimension of this topology, this has a topology, take the usual topology, and then dimension will be the disk. So you assume, so if X is, okay, so if suppose X is, so you start with irreducible topological space. You define it for irreducible topological space. Now if it is an arbitrary topological space, you have some finite union of irreducible ones. And you define dimension of X is the maximum of this, right? Then it makes sense, right? Okay. So this is a dimension. Now dimension of as a topological under this Zariski topology. Now if Y is reducible in the affine case, we know the dimension of Y is the dimension of the coordinate ring. So here it will be here also you can talk about the coordinate ring, but its dimension is one more. I'll come to that. Yeah. Okay. So I'll put some exercises. These are standard exercises. If you look at Hartshorne book, you will find it. The exercise. So please do these exercises. So basically, the exercise is prove Hilbert-Knudsen search. See, Hilbert-Knudsen search for projective variety. So as you remember that when we prove Hilbert-Knudsen, it has many steps, right? Weak and strong. So similar here also you have weak version and the strong version. So what is the weak version? So weak version is that suppose by the way, I should define something what is ideal of Y. So if so this is the definition before this. If Y is a subset of Pn, need not be closed or anything, then you can define I of Y. This F in S. Now when I write S of H, means homogeneous polynomials. Okay. This is called homogeneous polynomial. F such that f of p equal to 0 for all p belongs to Y. Now you check that this IY is a homogeneous ideal in S. S is your kx naught xn. So IY is a homogeneous ideal. But you have to be little careful with that because 0 is not there. So this homogeneous ideal by this way, if I start with a ideal, homogeneous ideal, you can talk about 0 set of the ideal. There you have to be careful because if you take the ideal, for example, x naught xn, this ideal you should try to avoid Because if you take the 0 set of this is nothing but point 0. But 0 is not a point in projective space. So always be careful in the projective situation that you should not take this ideal. So you should. So this is just a caution that when you do I of y, you don't get this ideal. This ideal you try to always. So whenever. Okay, I'll come to this again when I do put the exercise. But this is called ideal of definition, or ideal of definition of y, where y is a subset of Pn. So suppose this is a homogeneous polynomial.
But still, x not of x, that one is a homogeneous ideal.
Yeah, it's a homogeneous ideal, but that ideal is a bad ideal. It's not should not consider. Because that will give you point 0, which is not a point in the projective space. Homogeneous. Because see, when I talk about Hilbert-Null-Sensor, soon I will talk about the correspondence, right? The radical ideals and the points in projective space. Closed subset, irreducible closed subsets of projective space. But their radical ideal, this is also a radical ideal. This ideal I should remove. I should not take this ideal, because this ideal will correspond to 0.0. That point 0 is not a point in Pn, though it's a point in the affine space, but it's not a point. So that's why I am saying that be careful with this ideal. We should not take this ideal. So suppose
this is the ideal generated by x0, x1, x2.
This is a homogeneous ideal, but this homogeneous ideal always try to whenever you because this ideal is a bad idea. It should not be there. Whenever you study projective, okay. So suppose E is a homogeneous ideal. Then suppose f in S is a homogeneous polynomial. F is a homogeneous element. F belongs to SH. Such that f of p equal to 0 for all p belongs to. So now when I take homogeneous ideal, this ideal is not x0, x1, xn. Because otherwise it's not a point, there is no point, right? So that's what I am saying. So whenever I take ideal, I don't include that ideal, that maximal ideal. Such that so this will imply, what does Hilbert-Null-Sensor will say, that f power n belongs to A for some n. Proof is, go to the n plus 1, you go to the n plus 1, go to the affine case and try to do. Use the Hilbert-Null-Sensors for affine, and then.
So affine we can take for granted.
Yes. Use that. Use the affine Null-Sensor. So use affine Null-Sensors. So now for a closed subset, you know what is IY. So now you can define the coordinate ring. What is SY? Suppose Y is a closed subset, or suppose Y is any subset in Pn. Then you talk about the coordinate ring, the projective coordinate ring. So this is nothing but S modulo Iy. But Iy is a homogeneous element which vanishes on Y, which is a homogeneous ideal. This is a homogeneous ideal. You can talk about the quotient, and the homogeneity will this will give you also this Sy again it will be a graded ring, and because the degree will be because Iy will be a homogeneous ideal. Sorry, Iy will be a graded ideal. So it will be again Sy you can put a gradation. Anyway, let's not go into that. Let me state the theorem. So this is called homogeneous coordinate ring of homogeneous coordinate ring of Y. Now, point what I want to make, this is a ring. Now, dimension of, now Y is a topological space. Suppose you take Y is a, suppose is a Y is a closed subset or irreducible closed subset. You assume you closed subset or irreducible. That means Y is a projective variety. So now the point is the dimension of Sy. So Y is a topology, or it has a dimension, and Sy as a ring, it has a dimension, right? The point is the dimension of Sy and dimension of Y. So when Y is the whole Pn, then what is it? It is nothing but S, the polynomial ring, k x0, x1, xn. And what is that? Dimension. It's n plus 1. But the dimension of Pn is n. So it will be dimension of Sy will be dimension y plus 1. But in the case of coordinate affine case, it was dimension of Ay is same as dimension of y. Because here you have a one extra variable. When you are talking about n dimension, first of all, dimension of Pn, so you check this. Dimension of Pn is n. This is true because you have in a Pn, it is irreducible, Pn is irreducible. And you know that if you have a irreducible closed subset or irreducible topological space, if you take an open subset, dimension of U is same as dimension of the topological space, right? So this is some standard thing, that if X is a irreducible topological space and if U is a open, this is very useful. If U is open subset, then U is dense. So that means that means U bar is X. And dimension of U and dimension of U bar, they are same. So which will say that this is the same as dimension of X. So now you see that in Pn, you have these Ui's, which is isomorphic to An. These are open subset. Pn is irreducible. And the dimension of Ui is n. Dimension of An is n. So that will say the dimension of Pn is n. Right? But for a general variety, you see that dimension of Sy is dimension of y plus 1. So okay. So now these are also standard in affine case. You have seen this. If you take two subset y1, y2, and if you take the ideal of the homogeneous ideal Iy1, so this will contain Iy2, and I of y1 union Iy2 same as I of y1 intersection y2, y1, y2 any closed subset. sorry, what I am writing. Y1 union Y2 is Y1. And I of this standard we have seen a affine case. So, these are all the radical of A, and for any, sorry, not Z, V, I am denoting by V, right? V of I, A, sorry, I, Y, the Y closure in the projective space. If you take any Y subset of Pn, you take the, these are all the proofs will all follow, all proofs will follow the affine case, follow the same strategy as in affine. Fine. Situation. So, this is what, and then the correspondence that algebraic or projective algebraic subsets, algebraically closed subsets of Pn and homogeneous ideals, homogeneous radical ideals. In S. Of course, which are not, that ideal you have to remove, which are not equal to the ideal generated by. So, that is, you can write it as S plus, which is nothing but the degree S d greater than 0. Because if you have x0, x1, xn, that means all the polynomials are there, right? So, this is nothing but your x0, xn. Right. So, this is a one-to-one correspondence, and the correspondence is just, if you take y, you go to IY, and if you start with A, you take the 0 set. That is the correspondence. See, one thing we should know that I defined what is called quasi-projective varieties. These are most general object, in the sense that you take, if you, so these are open subset in some projective space. Now, what I write that if I take affine varieties, of course, and then you define what is called quasi-affine. So, these are open subsets of affine. Of course, if it is a affine, then it is a quasi-affine, right. So, in the category sense, that because AN itself is open in AN. So, affines, so quasi-affine means quasi-affine. Now, quasi-affine means open subset of affine. So, that means open subset in affine space. But affine is open in, affine space is open in the projective space. So, open subset of affine is open, affine space is open subset in projective space. So, a quasi-affine set is a quasi-projective set. Yeah, because see what I am saying, if X is affine variety, then X is in some AN, right? But quasi-affine means what? They are open subsets of affine varieties. So, X itself is open in X. So, affine varieties are quasi-affine. Quasi-affine means open subset in some affine variety. Affine variety is some close. So in particular, affine varieties, they are quasi-affine. Right? Now, if I take something in quasi-affine, so that means it is some open subset in some X, where X is in open so if I take something here, so that means this U is in X, some affine variety which is open, and this U I can think as this U is some open subset in AN intersection X. So this is a open subset in AN. So a quasi-affine corresponds to a open subset in AN, right? Because U will be some U prime intersection X, right? So a quasi-affine is a open subset in a affine space. But now affine space is open in projective space. So that will say that open subset is a quasi-projective, because AN is in PN open, right? Huh? U is open in X. So this you agree that if you take a quasi-affine set that corresponds to a open subset of AN, so you take that open subset. Yes, corresponding open subset. After all, you intersect with X, right? So you take the corresponding open. That corresponding open subset will be open in PN, because AN is open in PN. So in categorical language, when you are, you can define it. So I can think that quasi-projectives are most general objects, because when I think of a affine variety, I can think as a quasi-projective variety, right? And of course, quasi-projective will contain projective. So this kind of so now we will see that we are to define, so quasi-projective varieties are kind of most general objects which can be defined in terms of polynomials, right? Affine varieties, they are also defined by zero set of polynomials. Quasi-projectives are also, projective variety is also defined by zero set of homogeneous polynomial, and quasi-projectives are open subset there. So if we study quasi-projective varieties, if you understand quasi-projective varieties, then we understand lots of varieties, at least affine varieties, quasi-affine varieties, and projective varieties. So these are the most, I am saying that in the larger context, quasi-projectives is a very general objects, this quasi-projective varieties.